Okay, so welcome back. Uh, we want to look at this topic on MPLS VPN. MPLS VPN. So I'll begin by reading the foreword. So as hardware performance is improved, then MPLS no longer shows its advantages in data forwarding speed. Remember, in the previous topic, we said that we wanted to forward using MPLS rather than using the traditional IP header in order to improve data forwarding speeds. But now, as the processing power of routers improved, then that no longer became the obvious advantage of MPLS. However, MPLS is still widely used in new applications such as VPNs, virtual private networks, and also traffic engineering. So when we were doing HCIA, we talked about MPLS traffic engineering. Here we're not going to look into that. We're just going to focus on MPLS VPN. The reason as to why it's used is because it supports multi-layer labels. So you can nest labels and forwarding control separation. So due to the effects of traditional virtual private networks, many customer requirements cannot be met during network deployment. So we are going to see some of the problems of traditional VPNs. So MPLS VPN integrates two traditional VPN models, thereby promoting the development of virtual private networks. So by the end of this chapter, you should be able to. Mr. Gadudi, please help us read out the objectives.
Upon completion of this section, we will be able to models, master the working principle of MPLS VPN.
Yes.
Master the basic configuration of MPLS VPN.
Very good. Okay, so let's begin by looking at the earlier VPN models. Now, generally, first of all, you need to understand why VPN. Why VPN? So really, a virtual private network is used to connect private networks over the public network securely. So it provides security. So we can connect like a branch to the headquarters through the public network. Now, before VPNs, traditionally, companies used to use what we call dedicated lines, also known as leased lines. So what are leased lines? Leased lines are private lines. That means that if we want to connect this particular branch to the headquarters over the public network, we simply pay. We simply pay for a dedicated line. So a dedicated line has several advantages. For example, high security. Also, we have physical isolation between different users. So that really provides high security because you can actually see that, for example, this other user is using this particular line. And it's dedicated for that particular person only. Now, the major problem with this, as you might already have guessed, is that it's very expensive. And number two, most of the time, you're not going to consume the entire bandwidth or be using it. So it leads to wastage of bandwidth. So most of the time, your line will just be underused or not used at all. For example, during non-working hours. So banks used to interconnect using dedicated lines, also known as leased lines, but they're very expensive, and they lead to waste of bandwidth. Now, so they had to develop what we call bandwidth sharing technologies. Bandwidth sharing technologies. Some of these technologies are what we studied earlier, frame relay technologies, and also another one called X.25. So these technologies support logical isolation to establish a dedicated tunnel across the public network for communication between two sides. So generally, with frame relay and X.25, you can share. You can share. You can actually share the bandwidth through your carrier network, and you can create a logical tunnel, that is interconnecting, for example, your headquarters and the branch. So this indeed will provide isolation of data and also security, because these tunnels are invisible to each other. So that was one of the earlier technologies that was developed in terms of sharing bandwidth, because we are using the same channel or lines to forward data. Okay. Now, enterprise users can access the carrier network. So let's say here, so this is the carrier network. The carrier network is simply the network for your internet service provider. So you see here, we have client 1 HQ and client 1 branch. Here we have client 2 HQ and client 2 branch. Now, with this kind of setup, we have three types. We have three types of routers, which you must understand at this point because we are going to be referring to them as that. Now, the routers that are on the client end, these routers that are on the client end are referred to as customer edge. Customer edge routers, commonly referred to as CE. So we're going to be talking of CEs. So that is what a CE is. Okay, then we have this other router here, like RTC. Sorry, what did I do? Okay, so we have this router here, RTC, and also RTE here, the ones that connect to CEs. These ones are referred to as the provider edge. Provider edge routers. So we'll be referring to them as PEs. So RTC and RTE, they are PE. Yeah. Then we have this guy here, RTD, which is interconnecting the PEs in the carrier network. And this guy is normally referred to as the provider router. Provider router is also commonly referred to as the P device. So it's important that you understand these three types of routers, because when we create the VPNs, we are going to be referring to the interconnection between the C and the P, the interconnection between the P and the P, and so on and so forth. So it's important that you remember what a customer edge router is, what a provider edge, and what a provider router is. Please mute your mic if you can. Now, the other thing I need to mention is that the CE, the customer edge device that is located, the customer edge device is located in what we call a site. Is located in a site. So the site is simply the customer's premise. So a site is a group of IP systems with IP connectivity that can be achieved independent of the carrier networks. So for example, if at Multimedia University our carrier network is KNET. KNET is our ISP. So MMU is a site. KNET also provides internet connection to all the other universities. So KU is a site, UON is a site. So the customer device edge, the customer edge router is located in what we call a site. So a site, they'll have their own independent IP network, and they can do their own configurations within their private network. Okay. So let's look at several traditional VPN models. Generally, we have two, and we're supposed to understand their advantages and also disadvantages. So we have what we call an overlay VPN model. We also have what we call a peer-to-peer VPN model. So we need to understand these two and their advantages and disadvantages. Okay. So when it comes to overlay VPN, when you create a VPN using frame relay, so you're creating a tunnel. You're creating a tunnel over the public network to interconnect two private networks, like a branch and the headquarters. So when you're doing that, that is what we call an overlay VPN. You can create overlay VPNs using frame relay or GRE or IP security, or you can also use SSL, Secure Socket Layer VPN, to create an overlay VPN. As I've said, an overlay VPN simply establishes a tunnel between two CE devices, like what you're seeing here. So between two CE devices, like between the headquarters and the branch. You can also create an overlay VPN between two PE devices. You can also create a tunnel between two PE devices. Now, when you create a tunnel, like what you're seeing here, between CE1 and CE3, when you create a tunnel between CEs, you have certain advantages. One of the advantages is that customers can use overlapping address spaces. So overlapping address spaces means these customer here can use 192, for example, .168.1.0/24. And these customer can use the same, can also use that one, 168.1.0/24. So they can use overlapping address spaces. Of course, when you're doing so, again, we have total security because it's end to end between your own routers. So those are some of the advantages of creating an overlay VPN between CE devices. The disadvantage of creating, the main disadvantage of creating an overlay VPN between CE devices is that the VPN is static, meaning it cannot reflect network changes in real time. So in case a problem occurs within the carrier network with one of the routers along the path of the VPN, then it means that you have to manually set up connection. If you add a new site, again, you have to manually set up connection to that new site. So the management of this kind of VPN is quite difficult and complex. Now, on the other hand, you can also create VPNs, as we said, between PE devices. You can create a tunnel between two PE devices so that you can directly now transmit route information through the carrier network. The advantage of this is that it is dynamic in nature. So in case there is a problem even within the carrier network, it can always cater it can always create new routes within the carrier network. It also offers great confidentiality and security. The disadvantage of this is that you cannot use the same. Your customers cannot use overlapping address spaces. Because how will the PE distinguish between 192.168.1.1 from this customer 1 and from customer 2? So when you create such like VPN, you cannot be able to use overlapping address spaces. So that is the main disadvantage of that. Okay. So the other VPN model is what we call peer-to-peer. Peer-to-peer VPN. So let's look at the characteristics of a peer-to-peer VPN. So peer-to-peer VPN has the following features. So the CE and PE device exchange VPN route information. So as you can see here, CE1 and PE1 exchange VPN route information. So for example, for customer 1, you're creating for them a VPN instance called VPN1, like that. Then the PE device transmits VPN route information over the carrier network. So that VPN information will be transmitted by the PE device over the carrier network. So implementing dynamic VPN deployment and route advertisement. So different from the static overlay. So overlay VPNs are static, but peer-to-peer they're dynamic. So peer-to-peer VPN can be deployed on a large scale. So that's one of the advantages of peer-to-peer VPNs. Now here we actually, the two customers are sharing the same. They're sharing the same PE device. So we call this a shared mode. A shared mode. Now let's look at the next example here, where each customer, for example, so you can also deploy a peer-to-peer VPN like this. So where each customer is connected to its own PE device. So every customer is connected to what we call a dedicated peer PE device, provider edge device. So again, the main advantage with this is that you do not need to configure filtering, filtering of routes in order to differentiate the routes that are important. You see here, when you're using a shared PE device, you have to configure filtering of routes using SELs and NATing in order to import routes from customer 1 and customer 2 into the correct VPN instance. But when you're using a dedicated PE device, you do not need to configure that because you're using different routers. So you don't need to configure filtering of traffic, and therefore the configuration of using a dedicated PE device is quite simple, and also the management is simple. The main disadvantage, as you might already have guessed, is that, of course, routers are expensive. And therefore, if you have to if you have to buy a new router for every customer that you connect to, then you see that will lead to very high costs. It will lead to very high costs. So that's the main problem with using a dedicated. So those are the two models, VPN models, peer-to-peer and overlay. Now, the main problem again with the two models we've looked at is that they cannot use overlapping address spaces. So that is what MPLS VPN is going to provide. So let's look at MPLS VPN benefits so that you understand how it works. So you can see customer one here has VPN 1 and is using the address 172.1.1/32, and customer 2 is also using 172.16.1.1/32. So that is one of the main advantages of MPLS VPN. So two VPN users have the same address space. So devices on a traditional VPN cannot identify route information of the two users. So traditional, they cannot be able to do so. And if they can actually be able to do so, but the configuration and the implementation is very complex, very complex. So that's why we go the MPLS VPN way. So which VPN user does 172.16.1.1 belong to? You see, that is a problem that the PE device has to deal with, because CE2 and CE1, they are going to advertise this network because both of them are using the same network range. So PE1 has to know which one belongs to which one. So how to do that is what we're going to learn in the coming slides. Okay, so that is what we call address space overlapping. When two customers are using the same address space range, so it's called address overlapping. Now, in address overlapping, in order to address the problem, you have to address these three questions. These three questions. The first one is here. So, how does the PE device differentiate the same route from different VPN users? So how do I know that 172.162.1.1 is from CE1 and not CE2? Yet CE2 has also advertised the same. So that's the first thing you have to answer. Now, on PE2, because we're also going to advertise these networks over the carrier network, we are going to advertise this route. As you can see, the dotted arrow here is the route advertisement. So CE are going to share it with PE1, then PE1 is going to advertise within the carrier network until PE2 gets these two networks. So on PE2, how can the receiver PE device correctly import VPN routes when conflicting routes are transmitted on the public network? So how will the PE import 172.16.1.1 to VPN1 here and import this one to VPN2? So that's the next problem. Then the last problem that we have to answer is this one here. How can the PE device correctly forward received IP data packets to the target VPN user? So for example, we've done a ping. We've done a ping to 172.16.1.1. So we've done a ping. So the ping will be sent to PE1. So on a device here, from this router here, we've done ping 172.16.1.1. So how does PE1 know whether to ping this network or this network. So that's the other problem. So we are going to look at how to solve each of those problems step by step. Okay. So the very first problem was the problem of local route conflict. Local route conflict. That is, here we are using dedicated PEs. But you see, in the previous slide, for example, we have this scenario where we are using a single PE. So how do we know? How do we know whether this address is from this customer or this other customer? Now, generally, devices on the backbone network have their own responsibilities. Now, PE devices only saves its own VPN routes. Now, PE devices will have what we call a VPN routing table. So you can see here, this one has a VPN2 routing table. This one has a VPN1 routing table. Now, on the other hand, the P device, the provider device, saves only public network routes. So public network routes is simply the routing table, the global routing table. So P device will only save the global routing table. But the provider edge devices must have a VPN routing table. So that each network that is advertised from that particular network is actually linked to that particular VPN instance, as you're going to see in a short while. Okay. So let's look at this scenario here, where we are having a single PE device. Now, VRF. So VRF is what we call a VPN routing and forwarding table. So you're going to be seeing VRF. Now, VRF is a VPN routing and forwarding table. So how is it used? Now, each PE device will create a VRF instance. Will create a VRF instance for each of the VPNs. So you see, so really we are simply creating a table for VPN1 and a table for VPN2, like that. And of course, in the PE device, we also have a global routing table. So what we're saying here is that VRF can be enabled on a shared PE device in order to isolate overlapping routes. So what that means is 172.16.1.1 from CE2 will be saved in the VPN2 routing table. 172.16.1.1 from CE1 will be saved where? In the VPN1 routing table. So each shared PE device maintains multiple VPN routing tables, and of course one public network routing table, which is what we are calling here the global routing table. So that is how we can distinguish between the conflicting address spaces. Okay. Now, distinguish conflicting routes during route advertisement. So let's look at this example here so that we can understand it. So as you can see here, CE1 and CE2 are both using the same address space, and both of them are going to advertise at these particular addresses to PE1. Now, as we've said already, PE1 is going to create VPN VRFs, which are VPN routing tables. So for VPN1, and save that there. And they're also going to create a VPN2 instance and save that route there. Now, after doing that, they are going to transfer these particular routes into what we call a VPN v4 routing table. Now, what is a VPN v4 routing table? Now, a VPN v4 routing table maps a particular unique, a particular address with an identifier which we call a route distinguisher, or RD, a route distinguisher. So before a VPN route is advertised to the global, so now we want to advertise this route and this route to the global routing table. So how, in the global routing table, how do we differentiate these two routes? And they have the same, they're actually the same address from different VPNs. How do we advertise them in the global routing table? So to do that, we use a route distinguisher. So what is a route distinguisher? A route distinguisher is a globally unique identifier that is bound to the route in order to distinguish conflicting private routes. So kazi ya route distinguisher ni ku distinguish conflicting private routes. So please remember that we use a route distinguisher before we advertise private routes from the VRF to the global routing table. Now, when we map an IPv4 address with a route distinguisher, then we normally refer to that particular address as a VPN IPv4 address. Alternatively, we normally shorten this to VPN v4. So that's why here we are calling it a VPN v4 routing table. So when we map a routing distinguisher with a private address, then we call it a VPN v4 address. Okay. Any question, by the way? Any question? Okay. So let's look at this particular scenario. Now here we have branch 1 and branch 2. We want them to be able to talk to the headquarters. Now, look here. RDs can distinguish conflicting routes in the global routing table. But how can conflicting routes from different branches be imported to the VRF of the headquarters? So on this PE, how can we get these routes? You remember we injected these routes, VPN v4 routes. We injected them on PE1. So how can they be injected back to PE2 from the global routing table to VRF? How can we do that? Now, generally, RDs, route distinguishers, cannot correctly import routes to VPN. So we cannot be able to import from the global routing table to the VRF table. using RDs. Reason being, on each of the routers, we are going to configure an RD. And on this particular router, that is at the headquarters, we are also going to configure an RD. Now, an RD usually has a local scope, meaning it's unique within the local PE. It has to be unique within the local PE. So we can also configure this with 1.1. Now, the only route that PE2 can import to the HQ VPN VRF table is the one that matches the RD. So you see, we are only going to import this route that has an RD of 1.1 because it matches our own. So this other route is going to be lost, meaning branch 2 is not going to be able to access the headquarters. So how do we cater for that particular scenario? So to import routes to the correct VPNs, so a tag needs to be specified manually. So before sending a packet, the local PE device adds the manually specified tag to the packet. So after the remote PE device receives the packet, it imports the route to the correct VPN based on the tag. So let's see how that is done. So that is done using what we call a route target. Now, a route target attributes are used to correctly import routes to VPNs. Generally, we have two types of VPN target attributes. The first one is called the import target, and the next one is called the export target. So let me explain now what is happening here. Now, let me show you. So here we have set the export route target to 1:1, and the import to 3:3. Now, what does that mean? That means that when we are advertising this particular network, we need to specify the export tag as 1:1. So that's what you can see here, that this particular network from RD11, or RD from CE1 is 1.1, has an export target of 1.1. Now, when it has an export target of 1.1, on the headquarters, you are going to allow the headquarters to import 1.1. So when you've allowed the headquarters to export 1:1, then the headquarters, when it receives this route with an export value of 1:1, it's simply going to import it into its own VRF in the correct VPN. So similarly, for branch 2 here, you can see that for 2, again, we have an export value of 2:2. So you see here, 2:2. Then we are going to enable the router on the headquarters to import 2:2, like that. So 2:2 can also now be imported from the VPN v4 routing table to the VRF. So that is how this PE device is able to import routes from the VPN routing table, VPN v4 routing table, or the global routing table, to the VRF table. So it uses the route target. Now, on this one, we've used export 3:3 in the headquarters, meaning when the headquarters advertises any routes, it's going to have an export of 3:3, and this guy is going to import it because we've configured an import route target of 3:3. This guy is also going to import routes from the headquarters because we've also configured it with an import value of 3:3. So really, that is how the route target is used to import routes from the global routing table to the VRF. So I hope that is clear. Any question? Any question? Okay. So generally, when route targets are used to import routes to VPNs, the following conditions must be met. As you might have already seen, that the local export target must be equal to the remote import target. So let's look at the example in CE1. So our export target is 12:3. So in the headquarters, we must import. So the remote import target must be 12:3. On the other hand, when the import target, local import target, should be equal to the remote export target. So you can see that. Okay, so let's move on. So maybe just to explain here again, when we want to import from VRF to VPN v4 routing table, we use the route distinguisher to distinguish the routes. We use RD 11 and 22 here, 2:2. On the other hand, to enable this PE to be able to import from VPN v4 routing table to the VRF table, when we are advertising the routes, we have to specify an export target. So when we specify the export target, when they reach here, they can now be able to be imported from the VPN v4 routing table into VRF. So we use route target for VPN routing table to VRF. We use RD for VRF to VPN v4 routing table. So it can take time to understand some of this concept, but I'm sure with a second read, you can be able to understand it better. Okay, so what else? Solution to conflicting routes during data forwarding. Okay, so what do we have here? Okay, this is the third problem that we were talking about. If you do a ping from CE3, how will P1 know whether to ping this guy or this guy? So I want to access 172.16.1.1 because when you do the ping, the packet here, the ICMP packet, does not carry any identifier tag. So I want to access 172.16.1.1. So am I going to search the routing table of VPN1 or search the routing table of VPN2? So the packet does not carry any identifier. Therefore, when the ICMP packet arrives at PE1, PE1 does not know where to search. Do I search in VPN1 routing table or VPN2 routing table? So how do we solve that problem? So we solve that problem by using MPLS labels. By using MPLS labels. Let me show you. So what happens is, when we are advertising from VRF to the VPN v4 routing table, we use a label, an MPLS label, for each of the routes that we are advertising. We use an MPLS label. Now, generally, we are going to be using label nesting, meaning you are going to use more than one label. So we have what we call the outer label, the outer MPLS label. This outer MPLS label is also referred to as the public network label. The reason as to why it's called the public network label is because it's the label that is used to forward the data over the MPLS network in the carrier network here. So it's the one that is used to forward the data here. And so the outer label. Then we have the inner MPLS label. The inner MPLS label, on the other hand, is referred to as the private network label. The private network label. Why is it referred to as the private network label? Because it's used to forward data to the corresponding VPN. It is used to forward data to the corresponding VPN. So I'm going to show you how we use these two labels, the outer label and the inner label, respectively. But in this particular instance, please understand that each of the networks is going to have a unique label, because when we are creating a tunnel, an MPLS tunnel, each FEC will have its own label mapping. So they're going to have different labels. Okay. So how? That's the end. Okay. So let me explain. Now, when you do the ping to 172.16.1.1, this particular PE device, because it has this in its table, is going to use that particular label, and therefore, when this other PE receives that particular ping packet, it's going to check the label and know that this label 1026 is for VPN1, and therefore it's going to send that particular packet to the correct CE device by looking at the label, because if it came with 1027, then it would have forwarded it to VPN2. So that's how it uses that. I'm sure on the coming slides, we're also going to see how the outer label is also used in forwarding that particular packet in the public network. Okay, so now let's look at the MPLS working principles. Okay. Okay, so the working process of MPLS is divided into two steps. So the first one is MPLS VPN route advertisement. route advertisements. So after advertising the routes, so you can see here with this particular dotted arrows, we are simply advertising the routes. So CE will advertise to PE, then PE will advertise to P, P to PE like that, and then PE to CE again. So that's how routes are advertised. Then after that, after you've advertised routes, then you can be able to forward MPLS data. Can be able to forward MPLS data. So you can see that after advertising the routes, we can be able to forward the MPLS data. Now, this is achieved through four phases. Now, the first phase is what we call route information exchange. Route information exchange between the CE and the PE. So we need to advertise routes between the CE and the PE. So that's the very first thing we have to do. Then the next one is VRF. VRF route injection to what we call MP-BGP. BGP. Then number 3 is public network label distribution. So that is simply this is simply MPLS now. MPLS using LDP. Then the last bit is now MBGP route injection to VRF again on the other hand. So let me just explain this. Okay. So the first process there is this one here. So where we are sharing here, we are sharing the routes. We are advertising the route between the CE. So route information exchange between the CE and the PE. So that's the first process. The second process is VRF route injection to MP-BGP. Now, within the carrier network, they use what we call multi-protocol BGP to share routes, to distribute VPN routes. So they use what we call MP-BGP to share routes with VPN routes within the carrier network. Now, what you're simply saying there in step 2 is, you know that when we import a VPN route here, it's going to be stored in the VRF, the VPN routing and forwarding table. And after that, we have to transfer that route to the global routing table. And that global routing table actually uses MP-BGP. So that's what we are saying. And so VRF route injection to MP-BGP, like that. Now, after that happens, now this step here, where now MP-BGP is going to distribute that route to the entire carrier network. So that is now step number 3, public network label distribution. No, public network label distribution actually is creating a tunnel. I'm sorry. It's creating a tunnel. Now we are creating an MPLS tunnel to forward this particular data. So public network label distribution. Then the last one here is the reverse of what we did on step 2. So what we did here on step 2, now on this PE2, on the egress PE, if you can allow me to call it that, we now do the reverse. We now take the MP-BGP route and inject it to the VRF on PE2. So those are the 4 phases. So let's try and understand how they are done. So did I? Okay, let me see. Can I undo? No. Oh, okay. Okay, so let's see the first phase. So the first phase, as we said, is the exchange. the exchange of routes between the CE and the PE devices. Now, PE and CE devices can exchange route information through any of these methods. So you can configure static routes between CE and PE, or you can configure a dynamic routing protocol like RIP or OSPF or BGP or ISIS, whichever you want. So that is how routes are shared between the CE and the PE. Each one of them has a certain advantage. So during the lab, you're actually going to configure this. What you need to know is that most of the time, actually BGP is used as the routing protocol that supports route sharing between a PE and a CE. And because this router on the site belongs, for example, to a particular autonomous system. So in this particular scenario, we are going to use BGP because we are having different ASs. So we are going to configure BGP so that this can share routes. The other thing you have to do is to configure route distinguisher and route targets, which you're going to do during the lab. So I'm not going to show you right now, but we also have a lab scenario that we are going to look at in a short while. So we're going to see those commands. Okay, then the next step is to inject the VRF routes into MPBGP. So what that means is that we have VRF. It has VPN instances for each of the CEs that is connecting to the PE. So we now inject this into the global routing table. And that global routing table, we now call it VPN v4 routing table, because we have mapped and distinguished these private routes using an RD, a route distinguisher. So in this particular stage, a router adds an RD to an IPv4 route over VRF to change it to a VPN v4 route. Then a VPN v4 route containing a route, what do we call it? A route target. This one, route target, export a route target. So the VPN v4 containing the route target and label information is now added to the global routing table, which is what we're calling here the MPBGP routing table. Now, the routing protocol, the MPBGP routing protocol, is the one that is now used to exchange information between the PE devices. So that is what is going to share the information between those devices. Please disable your camera so that you can help us save on bandwidth. Okay, then after that, now it is the label distribution using MPLS, of course. So label distribution is step number 3. So the MPLS protocol runs on the carrier network to distribute public network labels. So it established channels to implement forwarding of VPN data over the public network. So what happens? The PE device runs the MPBGP protocol to distribute private network labels to VPN routes. Then the PE device correctly forwards the data to the corresponding VPN. Based on private network labels. Okay. Okay. So what does that mean? Let me just show you that. So this is simply LDP working here to distribute labels in order to create a tunnel. So as we know, for example, if the data is flowing like this, we know that LDP is going to distribute or share, is going to share the labels in this direction like this. So PE2 is going to tell P here that, hey, if you want to come to me, then use 1030, use 1030, like that. Then this guy is going to tell the other guy, if you want to come to me, use 3, like that. On the other hand, as you know, when a device is configured with 3, that is what we call the implicit null label. So it simply means it's going to do the penultimate hop popping. So it's going to remove the tag and forward the packet without the MPLS outer tag. So that is how the label distribution is done. Then after that, we now import, we now inject the MPBGP route to the VRF. We inject, so on PE2 here, we are now injecting from the global routing table to the VRF. So of course, the VRF will have the VPN instance for each of the VPNs. So it is the route target that is used to import each of the routes to the correct VPN instance table. So PE2 receives a VPN v4 route from PE1. Then PE2 checks the extended community attributes in the routes. So because we're using BGP, you remember we had the extended community attribute. So it's the one that carries these identifiers like the route target, the route target. Then PE2 compares the export target value, in the extended community attributes with the import target value of the local VPN. So if the two values are the same, then PE2 will import the VPN v4 route to the corresponding VPN routing table. So the corresponding VPN routing table. So that is how that happens. So we can now look at the data forwarding process, which happens in 3 steps. The first step is data forwarding from a CE device to the PE device. So that's the first step. The second step, which is what I told you, I'm gonna tell you how the outer and the inner label work. So the second step is the data forwarding on the public network devices. So public network is just the carrier network. Then the third step is the forwarding from the PE to the CE device. So those are the 3 steps. CE to PE, then public network, then PE to CE. So let's look at this. So what do we have here? Okay, so we have CE4 is sending a packet to PE2. So CE4 forwards data packet to PE2. So what happens? PE2 searches the routing table of VPN 2 to determine that the packet needs to be forwarded based on the labels. So it checks its VPN routing table. Then P2 then searches for the next hop and outbound interface and encapsulates the packets using MPLS based on the distributed label. So what is happening here? So it's going to check the VRF table for this particular VPN instance. So that's why it's being referred here to as VRF2 routing table. So it's going to identify that particular fake as any packet that is coming from that particular device. Then it's going to identify that, oh, this guy is supposed to be to go out as a labeled packet. So it's going to encapsulate it using an MPLS header and put the value 1030. It's also going to see the outgoing interface, outbound interface. So I'm supposed to forward it out through this interface, G0/0/0. Now, before doing that, it's also going to check the label forwarding information base. And it's also going to add another MPLS outer header now. The outer header is what is going to be used. No, this is actually the inner header, 1027. So this one here is the outer header, 1030, as you can see here. Then the inner header is this one, 1027. So this inner header is going to is the one that is identifying the mapping between this address 172.1.1/32 with VPN2. So you can see both of them, both of these are using the same address space. But how does this PE know that this packet is supposed to go to VPN2? So it knows that by looking at the inner label here. So the outer label is used for forwarding on the public network. The inner label is used to deliver it to the correct VPN instance. Okay, so let's see the next one, how it is forwarded on the public network. So on the public network, we can see the label forwarding table here. So on PE2, we added a label 1030. Now on PE3, we've configured it that when a labeled packet comes in with 1030, remove the label and forward it as a normal IP packet. So what that is going to do is that the P device here is simply going to remove this MPLS header. So the outer header is going to be dropped. We're only going to remain with the inner header because we have a value of 3 as the outgoing. That is the implicit null label. So it's going to remove that particular header, then look at the outgoing interface and forward it to PE1. When PE1 receives it, it's let's see what will happen. So it just has the inner MPLS label and the destination address there. So let's see. So you can see now from the PE device to the CE. So this one has received this packet with this IP address. So how does it know whether to send it to this guy or to this guy? So it checks that particular label 1027. So if it checks in its global routing table, it's gonna see that 1027, the next hop is CE2. And therefore it's gonna send it to this guy and not CE1. So that's how that inner label is used. That's why the inner label is called the private network label, while the outer label is called the public network, because the outer label is used for forwarding the data on the public network. The inner label is used for identifying the private network to which we are going to send that particular packet. if we are having conflicting IP addresses. So that is what happens. Okay, so now let's look at a scenario. Let's look at a scenario of MPLS configuration, VPN configuration. So MPLS VPN configuration example. So here we have the headquarters. We have the headquarters and we have two branches, branch 1 and branch 2. So what we want is branch 1 and branch 2 can communicate with the headquarters, but branch 1 and branch 2 cannot communicate with each other. So we just want to create a VPN, independent VPNs that are going to the headquarter. So correctly configure the devices based on information in the figure to allow headquarters users to access the branch users. So some of the information you can see here, for example, CE1 is connected via G000 on PE1. This one 001 to CE2, like that. So those are some of the things that we are going to be configuring. Also, it's important to look at the numbering, the IP addresses. They're actually using different addresses, which is okay. If they use the same, it will still be okay. The IP addresses between the C and the P, you can see here we're using 2.3, here we're using 1.3. So let's just go ahead and see how this is done. Okay, so as we said, the first step is to enable communication between the CE and the PE. So you can enable that by configuring any routing protocol. In this example, we are using BGP. So we are simply configuring BGP between CE1 and PE1, and between CE2 and PE2, between the headquarters and PE2. So the command for configuring BGP, as we know, so BGP 100. So we are doing this configuration on CE1. So BGP 100 because it's in AS 100. Then we want to peer. We want to peer to PE1 on 10.1.13.3. So on this particular interface, we're using the physical interface for peering. Then we advertise the network. So we want to advertise this network that we are attached to. We want to advertise that network so that it can be advertised to the headquarters, so that the headquarters can be able to ping 172.16.1.1. Then after that, we enable that. So that's the same thing. That's the same thing we are doing on these other devices. So I'm not going to explain those commands. So after doing that, the next thing is to configure IGP on the backbone network. So you need to configure IGP to allow the backbone network routers to be able to share routes. So in this case, we are configuring OSPF area 0. So I'll just show one example. For example, I can pick this one here, the provider device. So we're simply configuring it with the router ID, OSPF1, area 0. Then we advertise all the networks that are attached to it, and also the loopback interfaces like 4.4.4. So that is how we configure the IGP. I'm sure you've done that a number of times. Now, after that, we can now create the VPN instances. We can create the VPN instances on the PE devices. So CE1, we are creating VPN instance 1 for CE1, and we have to bind it to this particular interface that is connecting to CE1. So how to do that? We go to that router, then we create the VPN instance by using the command IP VPN hyphen instance, then the name of the VPN instance, which has to be unique. So VPN1. Then we configure route distinguisher, RD, so that we can be able to differentiate the networks. And we also configure route targets, RT, in the export and import. So VPN target 12.3 export like that. So you also have to do the same for VPN2, which is the VPN for CE2. Now, after creating the VPN instance, you now have to bind the particular instance to the interface that is connecting that CE. So you have to go to interface gigabit Ethernet 0/0/0. Then you do IP binding VPN hyphen instance VPN1. So we are binding this interface to VPN1 and binding the other interface here G001 to VPN2. So that is it about PE1. Let's look at PE2 here. So PE2 is configured, connected to the headquarters, which has a VPN3. So again, we create VPN3. Then we do a route distinguisher and a VPN target, export and import. Then of course we bind that VPN to that particular interface. So we go into that interface, then we use the command IP binding VPN instance VPN3. So after configuring the VPN instances, the next thing we have to do is to configure the MPBGP. So remember, the MPBGP is the one that enables the sharing of the VPN v4 routes to the PE devices. So to do that, we do BGP 500 because we are on AS 500. Then we want to peer to PE2. So PE2 is 5.5.5. This guy here is 5.5.5. So it's in the same AS. So we are going to form an IBGP. Then the connect interface is loopback 0. So we are using loopback 0 to create this BGP peering. So after that, we do use the IPv4 family, VPN v4. Then we enable the peering. So after we've done that, we go on and use this command, IPv4 family VPN instance VPN1 peer. So we're also creating a peering between this CE and the PE. So VPN instance VPN1 peer 10.1.13.1 is number 100. Similarly, we also create a peering with this one. Then on PE2, we peer with PE1. So BGP 500 peer 3.3.3. So this guy is 3.3.3. After that, we enable VPN v4 family, VPN v4, IPv4 family. Then we use policy VPN target, meaning that to import routes from the VPN v4, to import routes from VPN v4 routing table to the VRF table, then use the route target to do that. Then we enable the peering, and we also peer to that particular interface. Okay. So generally, that is all you need to do about MPBGP. Then the last thing now that you'll have to configure is MPLS. So in this case, we are using LDP to create an MPLS tunnel between those routers. So you have to begin by configuring manually. You have to manually configure an LSR ID. Please don't forget that, a very common question in the exam. So you have to manually configure an LSR ID, then enable MPLS, configure the MPLS protocol LDP by using the command MPLS LDP. Then you go to the respective interfaces, enable MPLS, and configure LDP. So you do the same for all the others. And after you've done that, that is it. That is it for creating the VPN. So now you'll be able to do the ping. So in the lab, you should be able to configure this and test the connectivity between the headquarters and the branches. So that is it about this topic. It's quite a long topic. It can also be confusing for the first time, but I want to encourage you to look at it again when you have time. It should not be very difficult when you give it a second pass and maybe a third one too. So volunteers to help us answer the first and the second question, please. Can someone help us with the first question?
Which of the following options are the technology of the overlay VPN model?
Overlay.
C. VPN.
Okay. So generally, traditional VPN models are overlay VPN and peer-to-peer VPN. So those are the two. Those are the two VPN models, overlay and peer-to-peer. Now, overlay VPN models can be created using IPsec VPN or SSL VPN or GRE, or you can combine GRE and IPsec. So the answer here is A, B, and D. Okay, thank you so much. Another person to help us with the next question. So which of the following options is used to correctly import MPLS VPN routes to the corresponding VRF? So do we use route target, route distinguisher? Just those two. Which one do we use, route target or route distinguisher? From the global routing table to VRF, do we use RT or RD? Yes? Okay, so you can revise that during your revision. Asanteni sana.